Next in section 1.1, limits, slide number 9, we are talking about how to evaluate limits without graphing. So far, we've only looked at evaluating limits graphically. So now, how do we do it without graphing? So the first thing that we're going to do is, number one, substitute the value that you are approaching into x. So we're merely going to do a calculation with the value that we're approaching. If you get a definite answer, then the limit equals that value. Now, that is not really common. We are going to have this other situation much more frequently. If you get 0 over 0, which is not a number, remember that is undefined, or infinity over infinity. This is called the indeterminate form. So what does that mean? That means that the answer is not determined based on the result of 0 over 0 or infinity over infinity, which I like to say means we have more work to do. So step 2, right? If we got the indeterminate form, then we are going to simplify the expression. So we're going to simplify the expression by one of two means. Number one, we're going to factor the expression, or we're going to multiply by the conjugate. Now, you'll recall these methods that we used, all right? And once we simplify by factoring or the conjugate, then we're going to revert back to step 1, and we're going to substitute the value we're approaching in to the new function that we've created. Then on step 3, we are going to, well, we're going to graph to check our answer. So very simple. Let's go ahead and do some examples. So it says determine the value of each limit without graphing. So when we look at this question, okay, we don't want to graph because, well, coming up with this graph by hand is, well, either a lot of work or sometimes it's just not possible. We just don't have the skills or the knowledge to come up with the graph. So what we're going to do is we're going to evaluate without graphing. So step 1, substitute the value that we are approaching. So we're approaching -2. So the limit as x approaches -2. So we're going to substitute that in for x into our function. So I get -2 squared minus 2 times -2 minus 8 divided by -2 squared plus 9 times -2 plus 14. All right, so -2 squared is +4 minus 2 times -2, that is plus 4 minus 8. That gets me 0 in the numerator. Divided by -2 squared, which is 4, plus 9 times -2 is minus 18 plus 14. So 4 minus 18 plus 14 is, of course, also 0. So 0 over 0, that is not a number. So that means we need to do more work. So the more work. All right, so I rewrite the limit as x approaches -2 because we have not evaluated. So now this one is one that we want to factor. So we see x squared minus 2x minus 8. So we want to factor that. All right, so that factors into x minus 4 times x plus 2 divided by the denominator. We want to factor that as well. X squared plus 9x plus 14. So factors of 14 are 7 and 2. So x plus 7, x plus 2. Now you'll notice here that x plus 2 is a common factor. All right, why is that? Well, because as x approached -2, if I plug in -2 plus 2, I get 0. And -2 plus 2 is 0. This is how we got 0 over 0. So if we get 0 over 0, it is a fact that there must be a common factor in the numerator and denominator. So when we find the common factor, we can reduce the function And we have a new limit problem. The limit as x approaches -2 of x minus 4 divided by x plus 7. So like I said earlier, we revert back to step 1. So revert back to step 1, we reevaluate. -2 minus 4 divided by -2 plus 7. So -2 minus 4 is -6, divided by -2 plus 7 is 5, -6/5. So the limit as x approaches -2 of x squared minus 2x minus 8 over x squared plus 9x plus 14 is -6/5. Now, if we were to graph, you could graph on your calculator to check this, but basically what we have going on here is we would have a vertical asymptote at -7 here, and we have a curve over here like this, and a curve over here like this or something, and we would have a hole in the graph at -6/5. So something like this would be our graph. All right. All right. So that is the answer to that limit. All right. Moving on. The limit as x approaches 3. All right. So now when we see a square root, we most likely are going to use our other method of simplifying, and that is using the conjugate. All right, so let's first of all do step 1, substitute what we are approaching. So the square root of 3 plus 1 minus 2 divided by 3 minus 3. All right, 3 plus 1 is 4. Square root of 4 is 2 minus 2 over 0. So 0 over 0. Once again, that means we have more work. All right, so the more work here. All right, limit as x approaches 3. I want to rewrite that because I have yet to evaluate the limit. All right, so I take what I had to begin with, x square root of x plus 1 minus 2, and I'm going to multiply by the conjugate of that irrational factor. So the conjugate, remember, is you take the sign between the two terms and switch it. So that means the square root of x plus 1 plus 2. And we're going to multiply that on top and bottom. Square root of x plus 1 plus 2. And then the denominator had the x minus 3 as well. So, sorry, x minus 3. So now we want to multiply out the numerator. All right, so if I do that, I get square root of x plus 1 times square root of x plus 1 is simply x plus 1. Now, when I multiply conjugates, I get minus 2 times the square root of x plus 1. And then I get plus 2 times the square root of x plus 1. Those are always going to subtract out. Then I get minus 2 times 2, which is minus 4. All divided by. Now, I do not want to multiply out the denominator. Why do I not want to multiply out the denominator? Because I know that x minus 3 must be a common factor, because once again, remember, I'm evaluating the limit as x approaches 3. And when I plugged in initially, I got 0 over 0. So that means x minus 3 must be a common factor, and ultimately it must reduce. All right, so continuing here, square root of x plus 1 plus 2. All right, so now I look at the numerator, the roots subtracted out. So I have x plus 1 minus 4, which is, of course, x minus 3. And so I notice that I have the x minus 3 in common, and I have the square root of x plus 1 plus 2. So now the x minus 3's do, in fact, reduce. Now, common mistake here is that people forget when I reduce the x minus 3 from the numerator, I have a 1 remaining. So 1 over the square root of x plus 1 plus 2. So now I revert back to step 1. I re-evaluate. So I re-evaluate. I get 1 over the square root of 3 plus 1 plus 2. So 3 plus 1 is 4. Square root of 4 is 2. 2 plus 2 is 4. So my answer is 1/4. Now, to verify graphically, well, what would this result tell us? That whatever that graph happens to look like, as x approaches 3, I'm going to have a hole in the graph at 1/4, right? So we want to make sure that if we were to graph this, we would see that there is a hole in the graph at that point. How do we know it's a hole? Well, because when I evaluated at x equals 3, I got 0 over 0, which is an undefined number.